Welcome to the session on numerical integration. In the previous sessions, we discussed the numerical integration. We derived the general quadrature formula, namely Newton's Cotes general quadrature formula, and then by substituting for n equal to 1, we derived the trapezoidal rule of integration as integral from a to b y dx is equal to h by 2 into y naught plus yn plus 2 times y1 plus y2 plus y3 plus etc. plus yn minus 1. By putting n is equal to 2, we derived the Simpson's 1/3 rule as integral a to b y dx is equal to h by 3 into y naught plus y2n plus 4 times y1 plus y3 plus etc. plus y2n minus 1 plus 2 times y2 plus y4 plus y6 plus etc. plus y2n minus 2, and by putting n is equal to 3 in the quadrature formula, we derived the Simpson's 3/8 rule as the integral from a to b y dx is equal to 3h by 8 into y naught plus y3n plus 3 times y1 plus y4 plus y7 plus etc. plus 3 times y2 plus y5 plus y8 plus etc. plus 2 times y3 plus y6 plus y9 plus etc. Here y0, y1, y2 etc., yn are the corresponding function values corresponding to the arguments x0, x1, x2 etc., xn. Now, here we shall discuss some examples of these three rules of numerical integration. First is dividing the range into 10 equal parts, find the approximate value of integral from 0 to pi sin x dx by using the trapezoidal rule and Simpson's 1/3 rule. Here the range is interval 0 to pi, ranges from 0 to pi, which is divided into 10 equal parts, means we have to take h is equal to pi divided by h, that is pi minus 0 divided by 10. We have to divide this interval into 10 equal parts, means each part is of length pi minus 0 divided by 10, that is pi by 10. We have to take h equal to pi by 10. Now, we compute the values of sin x for each point of subdivisions, that is the subdivisions are x is equal to 0, pi by 10, 2 pi by 10 etc. up to 10 pi by 10, that is pi. These values are tabulated like this, that is the x values are 0, pi by 10, 2 pi by 10, 3 pi by 10, 4 pi by 10, 5 pi by 10, 6 pi by 10, 7 pi by 10, 8 pi by 10, 9 pi by 10 and 10 pi by 10 means pi. And the corresponding values of y, that is corresponding values of sin x are sin 0 is 0, sin pi by 10 is 0.3090, sin 2 pi by 10 is 0.5878, sin 3 pi by 10 is 0.8090, sin 4 pi by 10 is 0.90 9511. Sin 5 pi by 10 is 1, that is sin pi by 2 is 1. Sin 6 pi by 10 is 0.9511. Sin 7 pi by 10 is 0.8090. Sin 8 pi by 10 is 0.5878. Sin 9 pi by 10 is 0.3090, and sin pi is 0. We have to tabulate the values of x and the corresponding function values like this. Now, by the trapezoidal rule, the formula for integration is integral from a to b y dx is equal to h by 2 into y naught plus y n, that is h by 2 into sum of the first and last ordinates. Y naught is the first ordinate, y n is the last ordinates, that is this is the sum of first and last ordinates plus 2 times the sum of remaining ordinates. Therefore, here this is x naught, this is x 1, x 2, etc., and the corresponding y values are y naught, y 1, y 2, etc. Therefore, by this formula we have integral from here a is 0, a means the value x naught and b is the value x n, that is here pi, that is integral from 0 to pi. H by 2, here h is equal to 0.1, sorry, h is equal to pi by 10, h is taken as pi minus 0 divided by 10, that is pi by 10. Therefore, integral from 0 to pi, y is here sin x dx is equal to h by 2, that is pi by 10 divided by 2 into y naught plus y n is 0 plus, this is y n, 0 plus 0, y naught and y n are 0, plus 2 times the sum of the remaining ordinates, that is 0.3090 plus 0.5878 plus etc. up to this 0.3090. That is equal to pi by 10 means pi by 10 into 2, that is pi by 20 into, here 0 plus 0 is 0, this is 2 times, this is equal to, one simplification we get 6.313, which is equal to 1.984 approximately. That is the value of integral, the definite integral from 0 to pi sin x dx is 1.984 approximately. Now, by Simpson's 1/3 rule, the formula for integration is this, that is h by 3 into y naught plus y 2 n, y naught is the first ordinate, y 2 n is the last ordinates, plus 4 times y 1 plus y 3 plus etc. plus y 2 n minus 1. Here the suffixes are the multiples of 3, y 1 plus and the multiples of, sorry, the suffixes are odd suffixes and 2 times y 2 plus y 4 plus etc. plus y 2 n minus 2. Here the suffixes are even. Therefore, by applying this formula, we get integral from 0 to pi sin x dx is equal to, this is by Simpson's rule. This is trapezoidal. Here integral from 0 to pi sin x dx is equal to h by 3, h is here pi by 10 divided by 3 into y naught plus y2n, that is 0.3090 plus the last ordinate is 0. Sorry, here y naught is 0. 0 plus 0 plus 4 times y1 plus y3 plus etc. up to y2n minus 1, that is here 4 into y1 is 0.3090 plus next is y3. y3 is 0.8090 plus next this is y3, y4, y5 is 1 plus y6 here y7 0.8090 plus next 0.3090 plus 2 times y2 plus y4 plus etc. up to y2n minus 2, that is y2 is 0.5878 plus y4 0.9511 plus y6 0.9511 next is 0.5878. H by 3 is common, therefore, this is equal to, in simplification we get the value of this is 2 approximately. If we use trapezoidal rule, we will get the value of this integral as 1.984 approximately, and if we use Simpson's 1/3 rule, we will get integral from 0 to pi sin x dx is 2. Both are approximately equal. Now, if we integrate exactly, we get integral from 0 to pi sin x dx. By actual integration, we get integral of sin x is minus cos x between the limits 0 and pi, that is minus cos pi minus cos 0. Minus is common, cos pi minus cos 0, that is equal to 2. Therefore, if we use Simpson's 1/3 rule, which will give more approximate value than the trapezoidal rule, here 1.984, but here we will get the value of the same integral is 2. By actual integration, the original value of this integral is 2. On comparison, we conclude that the Simpsons rule is more better than the trapezoidal rule. The next example is compute integral from 0 to pi by 2 sin x dx using Simpson's 3/8 rule of numerical integration. We have to evaluate this definite integral by using Simpson's 3/8 rule. Note that to apply the Simpson's 3/8 rule, the interval of integration 0 to pi by 2, here the interval is 0 to pi by 2, must be divided into a 3 multiple number of sub intervals of equal width. We have to divide this integral into a 3 multiple number of sub intervals in order to use this Simpson's 3/8 rule. Let us divide this interval 0 to pi by 2 into 9 sub intervals. We divide 0 to pi by 2 into 9 subintervals. 9 means 3 into 3, a multiple of 3. Therefore, we can use the Simpsons 3/8 rule if we divide this interval into 9 subintervals, each of width pi by 8. That is, width of each sub-interval is pi by 2 minus 0 divided by 9. That is pi by 18. Here h is equal to pi by 18. Now, we tabulate the values, x values and corresponding sign values. First value of x is 0, then pi by 18. Next is 2 pi by 18, 3 pi by 18, 4 pi by 18, 5 pi by 18, 6 pi by 18, 7 pi by 18, 8 pi by 18 and 9 pi by 18. 9 pi by 18 means this is pi by 2. The corresponding values of sin x are 0, 0.4 pi by 18, sin pi by 18 is 0.1736. Sin 2 pi by 18 is 0.3420. Sin 3 pi by 18 is 0.5. Sin 4 pi by 18 is 0.6428. Now, sin 5 pi by 18. Sin 5 pi by 18 is 0.7660. Next is sin 6 pi by 18 is 0.8660. Now, sin 7 pi by 18 is 0.9397. Now, sin 8 pi by 18 is 0.9848. And sin 9 pi by 18 is 1, that is sin pi by 2 is 1. Now, by the formula for Simpsons 3/8 rule, integral from here a is x naught, that is 0, and b is 9 pi by 18, that is pi by 2. Integral from 0 to pi by 2 sin x dx, y is sin here, which is equal to 3h by 8, that is 3 into h is pi by 18. 3 into pi by 18 divided by 8 into y naught plus y3n. Y naught is the first ordinate, y3n is the last ordinate. That is, we divided into 3 multiple number of sub intervals. Therefore, the suffix is 3n. Here y naught is 0 plus y3n is the last ordinate, that is 1, plus 3 times y1 plus y4 plus 7, etc. That is, starting is 1, next suffix is 4, 7, that is difference is 3. Therefore, 3 times y1 is here 0.1736 plus next is y4, y0, y1, y2, y3, y4 is 0.6428. Next is 0.9397 plus 3 times y2 plus y5 plus etc. Starting ordinate is y2 and y5, y8, that is the differences of suffixes are 3. Here y2 is y0, y1, this is y2, 3 times 0.242. Now is y5, y2, y3, y4, y5 is 0.7660 plus 0.9848. Sorry, this is y2, y5, y0, y1, y2, y3, y4, y5 is this. Next is y8, y6, y7 and y8. Okay, 0.9848 plus 2 times y3 plus y6 plus etc. That is, the suffixes are multiple of 3. Here y3 is y0, y1, y2, y3 is 0.5 plus y4, y5, this is y6, 0.8660, y6, y7, y8 and y9, that is 1. Sorry, these are 2 points. We already took the last ordinate one here, therefore here 2 times 0.5 plus 0.8660. On simplification, we get the approximate value as 0.9999887. That is, which is approximately equal to 1. Here we used the Simpsons 3/8 rule to evaluate integral from 0 to pi by 2 sin x dx. But if we integrate by actual method, the value of this integral becomes integral of sin x is minus cos x between the limits 0 and pi by 2, which gives minus cos pi by 2 minus cos 0, that is equal to 1. The value of actual value of this integral is 1. If we use this Simpsons 3/8 rule, we obtained the value of this integral as 0.9998857, which is very close to the actual value 1. Therefore, this Simpsons 3/8 rule is the best approximation for the integration, numerical integration, if we compare to trapezoidal rule and Simpsons 1/3 rule. Note that in order to use this Simpsons 3/8 rule, the total length will be divided into a 3 multiple number of subdivisions, which is a condition. Now, the Simpsons rule can be applied to find the volume of a solid. If the ordinates represent the cross-sectional areas at equal intervals, then the Simpsons rule gives the volume of the solid. Similarly, if the ordinates denote the velocities at equal intervals of time, then Simpsons rule gives the distance travelled. Simpsons rule is very useful to civil engineers for calculating the amount of earth that must be moved to provide a level highway or supplied to fill a depression or make a dam. Profiles of the earth's levels along different sections are prepared from surveys and contour maps, and the average height is calculated by the Simpsons 1/3 rule with respect to the desired level. From these figures, it becomes a simple matter to calculate the total volume of earth to be moved. Now, we have to do another example. That is, a curve is drawn to pass through the points given by the following table. The x values are 1, 1.5, 2, 2.5, 3, 3.5, and 4. The corresponding y values are 2, 2.4, 2.7, 2.8, 3, 2.6 and 2.1. Then find the area bounded by the curve, the x-axis and the lines at x equal to 1 and x equal to 4. Here the curve is like this. We draw dA. This is dA. This is the corresponding point is x equal to 1. We draw an ordinate at x equal to 1, and at x equal to 4 we draw another ordinate. Let this a point be xy. Now we have to find this area. We can use Simpson's 1/3 rule of integration. That is, area of the shaded region is integral from here 1 to 4 y dx is equal to, the curve is y, which is equal to h by 3. Here h is 0.5, that is equal to 0.5 into 0.5 divided by 3 into y naught is 2 plus the last ordinate is 2.1 plus 4 times y1 plus y3 plus etc. That is 4 times, this is y naught, y1, y2, y3, y4, y5 and y6. 4 times y1 is 2.4 plus y3 is 2.8 plus next is y5, that is 2.6 plus 2 times the remaining ordinates, that is 2.7 plus 3. Okay, this is equal to, on simplification, we get the area as 7.78 square units. Now we have to evaluate the volume of revolution about Yx, which is equal to pi into integral from 1 to 4 y square dx. In order to evaluate this integral, we just squaring all values of y, that is we evaluate y square corresponding to each points x. Then we use this rule of integration. We get the value of this as pi into 20.41 approximately, which is the volume of revolution about Yx. Now let me conclude this session. In this session, we just worked out some examples on numerical integration. First is we used the trapezoidal rule, and then Simpson's 1/3 rule, and the third is Simpson's 3/8 rule. Thank you for watching the class. Have a nice day.